brave students. I don't know what happens to the rest of them. Vectors in tensors in curved spacetime. So on Sunday, I spent 2 hours. It's a very mathematical lecture, which was maybe the most mathematical lecture there is. Which essentially I can summarize everything said in one sentence, which is that vectors are directional derivatives. We needed that to obtain back the sense of direction of vectors on the manifold. So remember the real goal was to define a vector space at Tp at the point P on the manifold using only things that are intrinsic to the manifold without the need to get outside of the manifold. Right? And we said that basically the only thing that is intrinsic to the manifold is curves along the manifold. And we can look at these curves as being basically mappings. Right? If I have a curve, this is my manifold and I have a point P on the manifold, I can look at a set of all curves that go through P. So something which is very legitimate. And then if I'm thinking of a curve, which I'm specifying it by some parameter lambda, then really this is a mapping from R to M. And I can similarly think of a function in the vicinity of P, which will be a mapping from M to R or to Rn. And essentially what we did was to define a vector as the operator of these functions. Right? And the simplest way is to think of it, okay, so the curve really, if I have some function f, which is defined at P in the vicinity of P, I can think of I can think of this directional derivative as a mapping from f, or operator that maps f to df d lambda, basically. And this essentially gets all the properties that we want for a vector space. So the bottom line was that the tangent space Tp can be identified with the space of all directional derivatives of all the curves or along all the curves through P. And we said it has basically all the properties that we want from a vectorial space. And that means that essentially when we speak of a vector v, we simply write the vector v as the components of v mu, and d mu would be the basis vectors. It's called the coordinate basis. So essentially, Doing that means that I'm looking at the vicinity of P and I'm drawing a set of coordinates. Right. X1, X2. I have d mu, dx1 and dx. And using that, transformation law of the components are essentially identical to what we had before. So when I'm switching from x mu to x mu prime, with different coordinate system, x1 prime and x2 prime, what we're going to get is that v mu prime dx mu prime over dx mu d mu. That's right. D mu. Which is essentially a generalization of what we did in special relativity. And then, but covariant vector is essentially the same. So for the covariant vector, uses a basis the gradients. The transformation was basically the same, it was the opposite. So covariant vectors omega mu prime dx mu over dx mu prime omega mu. Nothing else, and the same for and the same for tensors. And t mu 1 prime mu k prime mu 1 prime mu l prime. We exactly the same thing. Dx mu 1 prime over dx mu 1 dx mu mu k prime over dx mu k dx mu 1 over dx mu 1 prime dx mu l over dx mu l prime t mu 1 mu k mu 1. So basically it's a copying of what we did with the special relativity, only now we do it in any arbitrary chord space. That's it.
But all of this is valid only in the vicinity of point P, right? We
want to define TP, tangent vector space, to P.
Yes.
Yeah, that's fine.
There is no connection between.
That's what we're going to do today. That's what
Because defining coordinate system only in one point.
No,
meaningless,
I know.
You know.
What I did was that vectors are directional derivatives. That was everything we did last time. I summarized everything in 4 words. Then we say tangent space TP. I can identify it with the space of all directional derivatives along all the curves that go through. That's it. I did not change anything from what I said. I told you I'm not going to do that. I said that vectors belong to the point P. Now you can do the same for any other point, right? Q, R, S. Choose other points, that's fine. But they're different vector spaces.
They don't know about each other.
Yeah, that's a problem. They don't know about each other. Okay? Today we'll start to find a way of fixing that. One step at a time. Before we're going to do that, I want to do some other things. So today it's going to be also slightly technical, not as much as it was on Sunday, but with some very important consequences. And actually we're going to see some surprising results which could make you, hopefully, make you happy. Okay, so any further questions?
Can we do the same procedure on flat space?
Yes, of course. The thing is, you will not see that on flat space. You only see that on curved space.
See what?
Okay. We said there are two things. I mean, first you can do everything we do here on a flat space. You can do the same definition, everything works out. In flat spaces, you don't feel the need for that in a way, because in flat spaces, it seems to you that you can easily take a vector from one point to another point, compare them, etc. Right? Here you cannot do that. Okay? And we discussed it already. Right? A vector space at point P, TP, right? The tangent vector space, and the tangent vector space to a different point Q, they are not the same vector spaces. So you cannot simply take a vector in P and move it to Q and then do something. Compare the vector from P and the vector from Q, say which one is longer. Add them, subtract them. You cannot do that. Right? What we did, everything we did, so this got nothing to do with what we did last time. It's got to do with the fact that a manuscript in general is not flat. What we did last time was getting back the notion of direction. Okay. Once I'm defining a curve and I'm saying that the vector space is associated with a directional derivative, so derivative along the curve, I know which direction it is heading at that point P, which is essential for what is to come, which is derivations. Let's get to that shortly. Okay, is that clear? So let's move on. Before we start to talk about derivations, I want to talk about something else, which is called volume elements and tensor densities. So the idea of tensor density and volume element. So let's look at the metric tensor, G, mu, and U. Transformation of the metric tensor. So first the metric tensor, theta alpha beta, d psi alpha, dx mu, dx beta over dx mu. Now we want to do the transformation from one coordinate system to another. So G, U prime, U prime. Eta alpha beta, d psi alpha over dx mu prime, d psi beta over dx mu prime. So eta alpha beta. I want to express that in terms of the G mu nu. So I have d psi alpha over dx mu, dx mu over dx mu prime, d psi beta over dx nu, dx mu over dx mu prime. Which is what? Dx mu over dx mu prime, dx mu over dx mu prime, G mu nu. Note that because I have here term by term, it's multiplicity of terms, and I got no problem switching the orders. Right? Don't forget, it's all, there are plenty of summations here. I'm summing over alpha, I'm summing over beta, I'm summing over mu, I'm summing over mu. Okay, so this is a covariant tensor, right? This is what the covariant tensor is expected to be transformed. So just add it anyways. Inverse of G, controvariant. We have the inverse of this one, so it's a controvariant. Yeah. Kronecker delta. That is mixed tensor.
Mixed by it's
One.
also variant.
Oh, it's a tensor. Just have one up, one dx mu prime, and then the second will be the opposite, dx mu
okay.
prime. Sounds good. Not everything is a tensor. Right? Unfortunately, in life is a bit more complicated. So not everything is a tensor. For the classical example, in a fine connection, gamma is not a tensor. We'll get back to it. An important quantity of something which is not a tensor, that goes back to your linear algebra course. I don't need to know if you learned it in linear algebra. The determinant of the metric tensor. G is minus determinant of G mu nu, or G mu in absolute values. You learn about determinants, of course. So this is not a tensor. Now we have the transformation law of the metric. So using transformation law of the metric, I don't know if you've ever seen transformation law of the determinants. Seen that before? That I have serious doubts. If you have, it's a linear algebra basically textbook. I don't know if you've been shown. So G of x mu prime is dx mu prime over dx mu minus 2 G x mu. Sometimes it's simply d x prime over dx minus 2 G x mu. What is this? Do you know? What do you call that?
Yeah.
This is a Jacobian. Okay, you've seen that. Okay, good. So this is a Jacobian. So dx prime over dx is the Jacobian. The matrix or transformation. Yeah? This is linear algebra 1? Or 2 or rings a bell. You have seen. Okay. Jacobian of the transformation from x to x. Okay. So what do we have here? That the determinant G transformed as a scalar, except from the extra factor of the Jacobian. Okay? And there is no transformation like that, which tells me it's a tensor. It's not a tensor. Plus this extra Jacobian. So G is called, G is a scalar density. And the number that we have here is called the weight.
It's minus 2.
Yes. So G is a scalar density of weight minus 2. Why is that important or interesting? Because if we are making a transformation of a volume element, so transformation of a volume element, so Vn x. Let's have a volume element, so I have the coordinates. And what happens when x is transforms to x prime? What happens to d and x? What? It gets a Jacobian, right? So Vn x prime is just dx mu prime over dx mu, Jacobian dnx. You see. So if I want to make it an invariant, what do we do? So what is the weight of that?
1.
1. So if I want to make an invariant volume element,
Multiply by the square root of
invariant volume element. I can just take that and I multiply that by square root of g. It's pretty cool. Example. Let's say I have a Euclidean space. Simple one. I just write it down in spherical coordinates, or theta 5. Right? So Vs squared, dr squared, plus r squared, d theta squared, plus sine squared theta, d phi squared. Right? What is G?
You have 1, the first one.
1,
R squared,
r squared,
sine theta
r
squared,
squared, sine squared theta,
and 0.
and the rest are 0. Right? dr, theta, d phi. Right? dr, theta, d phi. So what is the determinant of G?
R squared, sine theta squared,
R to the 4.
R to the 4, sine squared.
Right, just multiply all of these. So what is an invariant volume element? Okay. Okay. Surprise, surprise. Right? So it works. Invariant volume. Okay, I just say, okay, I put a small note here. We don't really need it, but it's just good for you to know. So when we have a metric, we write the metric. If we write the metric in the canonical form, it means the G mu nu, canonical form of the metric, means that G mu nu in the diagonal so -1 first, and +1, and then 0. It's for the metric in canonical form. If we have any eigenvalue of the metric which is 0, and the metric is degenerated, then we cannot invert it, so there's no inverse metric. If we don't have minuses but all signs are positive, then we call this metric to be Euclidean. Another name is Riemannian. If there is a 1 minus sign, then it's called a pseudo-Riemannian. Or Lorentzian. Because the metric we have in GR always pseudo-Riemannian. Okay, you see that? Just convert it into eta, which is always -1 plus plus. So just change transformation. Okay. One more thing I have to say about that is the Levi-Civita tensor density. Yes.
We said that determinant of the metric is not a tensor of rank 0 because it's not invariant. It changes during the coordinate summation. That's why.
It's called a tensor density, scalar density. If we had no Jacobian here, it would be a tensor. If it's just a number,
Yeah,
so we have this Jacobian.
number doesn't depend.
So the
Okay.
Jacobian is called, that was the density factor.
And the second question, is there any physical system that has degeneracy in eigenvalues if it's zero? In the metric?
It's not a physical system, right? So it's symmetric. It's how do you... the metric doesn't define physical system by itself.
Okay,
it
but
defines the space. So you're talking about the space in itself,
Yeah,
right?
yeah.
Space-time. Not in the course we're in. You need to go to higher dimensional theory as far as this is just for you to know that these things exist.
because
Here we are, here we are. We don't deal with all sorts of non-orientable manifolds and all that. You can mathematically you can use your imagination to come up with various crazy manifolds or spaces. For this course, no, we're going to limit ourselves to simple spaces.
Because I thought it can happen, in black hole, for example. Then you can, inverse, so you can go back.
We will,
to something.
don't worry. In a few weeks' time, you will know everything you need to know about black holes. Okay, we're getting one step at a time. Okay, believe we're going in that direction. Okay. The next thing that I wanted to discuss with you is about this Levi-Civita tensor density. You can guess that the way I write it, it's not a real tensor. So we had the Levi-Civita tensor, right? Symbol, mu1, mu1, was plus 1 if mu1, mu1 is an even permutation of 0, 1, and -1. -1 if this is odd permutation. And 0 odd ones. In fact, this is Levi-Civita symbol. Put a tilde on that because this definition is the Levi-Civita symbol. That's what it is. Because the way it is being defined, it has nothing to do with coordinate system. It just tells you what are the components here and will tell you whether this is +1, -1, or 0.
Is it tensor density or
So what happens when we're changing coordinates now? So epsilon tilde u1 prime, u1 prime. Again, it's a linear algebra textbook, which I don't know if you've seen that. I doubt, because I don't think this has been seen in standard, but you can just go on and read it. It's just extra dx mu over dx mu prime. It's an extra factor of the Jacobian, basically. Determinant epsilon tilde mu1 mu1 dx mu1 dx mu1 prime dx mu1 over dx mu1 prime. Which means that this is a tensor density of rank plus 1. So we want to work with tensors, what are the tensor densities? Every time we have some tensor density quantity and we want to turn it into a tensor, what do we do?
Use the square root of
Square root g to the relevant power. Okay. So we multiply to turn into a tensor. Multiply by g to the power weight over 2. So once we take that and multiply by g to the relevant weight, then we have the tensorial quantity because this Jacobian will just cancel out. So define whatever we submit a tensor to the epsilon u1 un is square root of g times epsilon u1. That's how we work with Levi-Civita tensors in curved spaces. And then if we want to have the Levi-Civita tensor with some upper indices, sometimes we want, right? It will be the same tensor density, so epsilon u1 un. It looks exactly the same, but now it's a tensorial density of weight of -1. So we turn it into a tensor, epsilon u1 un. We now have to take sine g and then over square root of g. Epsilon tilde u1. Okay. There's this aside which we're going to need when we want to make some calculations. All right. Any further questions about tensor densities? No? We're all happy. So now we're going to move on to the main thing we're going to do today, which is called covariant derivatives, which goes back to the thing we already discussed earlier. Can I erase that? Yes. Covariant derivatives. It'll be a little bit annoying, but it's just algebraically annoying. There's nothing conceptually annoying here. Okay. The goal is to write equations in physics. Right, in curved space. Nearly all equations in physics involve some sort of derivatives. And we have a great advantage of working in tensors and vectors because we know how they transform between different coordinate systems. So we wish that the derivative was also a tensor, but it is not. It's a sad truth that if we take a derivative of a vector, it is not a vector or a tensor. So if we have a vector v, consider the vector v transformation law. V mu prime is what?
Dou x mu prime, dou x mu.
Makes perfect sense. Now I want to take the derivative of this vector. So we'll take the derivative. But take the derivative. V mu prime dx lambda prime. D over dx prime of dx mu prime over dx mu v mu. So I have two terms. Let's take first the derivative of that, dx mu prime over dx mu. I cannot take directly the derivative of v mu with respect to x lambda prime because this is a new coordinate system, this is an old coordinate system. So the only thing I can do is to take dx rho, let's say over dx lambda prime, dv mu over dx rho. But now I have the extra term. Right? D squared x mu prime over, to take it with respect to x lambda prime, so I'll have to play a little bit of a nasty game here. Dx mu dx rho dx lambda prime times dv.
This fine connection then?
No. Looks a bit similar, you're right, but it's not. Good spot. This is what we'd expect to see if the derivative was a vector. Right? This is transformation of a vector. We have this extra term, which is unknown. So we need to somehow think of a way, because we do want to have this derivative of vector. Remember we had Euler's equation we wrote in the form d mu t mu equal to 0. So we want to generalize that. So we need to construct a way, some operator, which will transform vectors to vectors, or tensors to tensors, and reduce back to derivatives, to what the derivative is supposed to be doing. That is called covariant derivative. And as you already spotted, so we need an operator that transforms like a vector and reduces to normal derivatives in flat space. This is the code. That is called covariant derivative. What do we do? I'll get back to that, but right now we will indeed start by looking at the affine connection. The affine connection, gamma, lambda, mu, we call d x lambda over d psi alpha, d squared psi alpha over d x mu, xi. What it is? Locally, inertial coordinate system. X is what we change. So now we want to change coordinates. X mu to x mu prime. So gamma lambda prime mu prime is dx lambda prime over d psi alpha, d squared psi alpha over dx mu prime, dx u prime. Okay, now let's express that in terms of the old coordinate system. So we can write it down as dx lambda prime, what do you get choose here? dx rho over d psi alpha. That's that. Times d over dx mu prime of dx psi alpha dx mu prime, which I will write as d x sigma over dx mu prime d psi alpha over dx sigma. So dx lambda prime over dx rho over d psi alpha times, we're going to have here two terms. Let's do the derivative of that term first. So it will be dx sigma over dx prime, and then here I want to take just the coordinates with respect to the old ones. So it will be d, let's say x tau dx mu prime d squared psi alpha over d x tau dx sigma. Okay, this is taking the derivative of this part. Plus, now I have the derivative of the first part, so it will be d squared x sigma over dx mu prime dx nu prime times dx I alpha over dx sigma. But we have now the definition of gamma, which I can plug it in here. So that means that I have a gamma lambda prime mu prime is dx lambda prime over dx rho dx sigma over dx mu prime sorry, dx tau over dx mu prime. And this is just gamma rho tau sigma. This is just the first part. But now I have also the second part. Plus dx lambda prime over dx rho dx rho over dx I alpha over dx sigma is just a delta function. So I can, instead of sigma, I can replace with a rho, and I'm left with d squared x rho over dx mu prime dx mu prime. Okay. So if the affine connection was a tensor, this term would be what we would expect it to be. It's transformation law. But this term is annoying because it destroys it. But I can write this second term in a slightly different way. I'm going to do again a small mathematical trick. Again, It's annoying, but it's all algebra. So I take it like that. So let's see what am I going to do. I want to write this down in a slightly different way, so I'm going to use a trick, which is writing down dx lambda prime over dx rho, dx rho over dx nu prime is delta lambda prime nu prime. It's always true. And I'm going to take the derivative of that with respect to x mu prime. Of course, this is going to give me a 0, so I have two terms here, so I can simply equate them. And I'll write it down. Dx lambda prime over dx rho, d squared x rho over dx mu prime dx mu prime. Now there's a second term, so I'm transferring to the other side and put a minus sign. So it'll be a minus. Take now the derivative of this part, so it will be d squared x lambda prime over dx rho. And then you in terms of dx sigma, and then dx sigma over dx mu prime, and then dx rho over dx mu prime. Okay, go with me. Understand what I did here? Let's do the derivative. I have two terms here. This gives me 0. The second term is just equal to this. So I get the minus sign here. And I'm going to use that inside of that part here. So I'm going to write down gamma lambda prime mu prime as a dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime, gamma rho tau sigma, and then there will be a minus, and it's written here basically, dx sigma over dx mu prime, dx rho over dx mu prime, and d squared x lambda prime over dx rho dx sigma. Yeah, I love it as much as you love it. But remember, this is just algebra. I'm just doing playing with that. Just don't get mixed too much with that. Don't get mixed at all with the indices, and you're fine. Now what do we do? Now that I derived that, remember, what I want is to get something which looks like a derivative, right? Which is a tensorial. Still, I had a problem that the direct derivative of a vector did not give me anything which is tensorial, because it was a space structure, which you need to get rid of. So what I'm going to do now, I'm going to look at the transformation law of the affine connection times V. So I look now at gamma lambda prime mu prime times V mu prime. So this is equal to essentially what's written here. So dx lambda prime over dx rho dx sigma over dx mu prime dx tau over dx mu prime times gamma rho tau sigma minus dx sigma over dx mu prime dx rho over dx prime d squared x lambda prime over dx rho dx sigma times v nu prime, which information load be dx u prime dx kappa v kappa. Let's read it back. Yeah? You look stunned. Some of you. I just did that. Multiply by v. And look at how they transform. So again, I have two terms here. First term, this is dx lambda prime over dx rho. And I have a dx sigma over dx nu prime times dx nu prime dx kappa. So that's a delta sigma kappa. Right? So forget this for a second. Here I have a dx tau over dx nu prime. And the delta sigma kappa so I can write this as gamma rho tau sigma v sigma. Instead of kappa, I put a sigma. That's okay. That's the first term. For the second term, I have a minus dx sigma over dx nu prime. And dx rho over dx nu prime over dx kappa means there is a delta rho kappa. So I just write down d squared x lambda prime over dx rho dx sigma v, I'm going to say rho. It's okay. Now I just want to make a slight change in notations. I want to slightly switch notation here. I want to switch mu prime and lambda prime. And then, so every place I have a mu prime, I'll have a lambda prime. So then I have a gamma mu prime lambda prime nu prime v mu prime. So dx mu prime over dx rho. Dx tau over dx lambda prime gamma rho tau sigma v sigma minus dx sigma over dx lambda prime d squared x mu prime over dx rho dx sigma v rho. It's okay, I just changed the indexes. Okay, I want to make another small change of indexes. Here I want to replace rho with mu. Rho just goes to mu, and sigma will be a rho. And here I want to replace, sorry, tau would be a rho. That would be rho. And here I want to replace rho with mu and sigma with rho. Again, I can do that because these are all dummy indices.
Yeah.
So it's perfectly legal. So I can write this as dx mu prime over dx mu. Tau now becomes a rho, so dx rho over dx lambda prime gamma mu rho sigma v sigma. That's the first one. Minus dx rho over dx lambda prime d squared x mu prime dx mu dx rho v mu. Okay? I just play a little bit with the indices. Everything is totally legal because all the indices are dummy indices. Why on earth did I spend time doing that? Because remember our starting point of this entire discussion which was that d v mu prime over d x lambda prime was dx mu prime over dx mu, dx rho over dx lambda prime, dv mu over dx rho, plus d squared x mu prime over dx mu dx rho, dx rho over dx mu lambda prime times v mu. Did you write that? Now what am I going to do? Add it. Right? So now if I have d v mu prime over dx lambda prime plus gamma lambda prime, so mu prime lambda prime mu prime v mu prime this and this cancel out, right? And what goes left is dx mu prime over dx mu, dx rho over dx lambda prime times dv mu over dx rho plus gamma mu rho sigma v sigma. Ta-da! What did we get?
Tensor.
Yes. This quantity here transforms like a tensor. This is how we expect the tensorial quantity to transform. Okay. So this is called the covariant derivative. This is a covariant derivative of a vector. And it has several notations. So one notation is like that. Mu, mu. Oops. This is lambda v mu. Another notation which I often use is v mu semicolon lambda. Remember with the derivative we just said v mu comma lambda. This will be a semicolon lambda. Okay, which is exactly what is written here. dv mu over dx lambda plus gamma mu lambda sigma v sigma. And this is a tensor. Since v mu prime lambda prime transformed as dx mu prime over dx mu, dx rho over dx lambda prime v mu rho. In flat space-time, what is the affine connection?
Zero.
Zero, right? So we show the affine connection depends on the derivatives of the metric. It's all zero.
No,
So
but
this
if
reduces back.
If it's polar coordinates,
Well, we'll see that.
it's not zero.
We'll see that. Okay.
That's some terms.
Yeah, it's fine. We'll see that. Don't worry, we'll discuss that shortly. Today, I'm pretty sure we'll have time. Well, I hope we'll have time. I think we'll have time. Okay. Okay. But let's do first, continue on with the derivation. We haven't finished yet, so we'll keep on discussing more physical insight. What about the covariant vector? Covariant derivative of a covariant vector. Remember transformation of a covariant vector. Omega mu prime is dx rho over dx mu prime omega rho. If I take the derivative of that, d omega mu prime over dx mu prime. Let's first take that one. So this is dx rho over dx mu prime times d x sigma dx mu prime d omega rho over dx sigma. That's because we cannot take omega rho directly. Derivative is x prime plus d squared x rho over dx mu prime dx mu prime omega rho. But we had previously, remind you that we had the transformation of the affine connection, gamma lambda prime mu prime dx lambda prime over dx rho dx sigma over dx mu prime dx tau over dx mu prime gamma rho tau sigma plus dx plus dx lambda prime over dx rho d squared x rho over dx mu prime dx mu prime, which we derive. So what do we do now? Subtract. Very good. So if I have gamma lambda prime mu prime omega lambda prime dx lambda prime over dx rho dx sigma over dx mu prime dx tau over dx mu prime gamma rho tau sigma plus dx lambda prime over dx rho d squared x rho over dx mu prime dx mu prime d x kappa over dx lambda prime omega kappa dx sigma, gonna have your delta kappa rho dx sigma over dx mu prime dx tau over dx mu prime gamma gamma kappa rho, so it's kappa here, tau sigma omega kappa plus again tau kappa rho, so let's say d squared x kappa over dx mu prime dx mu prime omega kappa. These two terms here. So what I need is to extract. Then we get a d omega mu prime over dx mu prime minus gamma lambda prime mu prime omega lambda prime. Good here. Oh, fine. Just instead of tau, I can write here a rho. Okay, this is bigger. So I have this to be dx rho over dx mu prime dx sigma over dx mu prime time d omega rho over d sigma minus gamma over sigma omega. So covariant derivative of a covariant vector. Lambda mu omega mu semicolon lambda is d omega mu dx lambda minus gamma sigma lambda mu omega sigma. Pretty cool, isn't it? Yeah. One is a plus, one is a minus. That's all. And generalizing that to any tensor of any rank is pretty much straightforward from here on. Right, so if I have any tensor, so covariant derivative of the tensor t mu1, let's say mu2, mu1, semicolon sigma. What is that? We start by a regular derivative, t mu1, mu2, mu1, comma, sigma. Right? And then for every upper index, there is a plus gamma. Right? What's going to be in the upper index? So it's going to be mu1, right? Then the sigma, and then the gamma index. Lambda, t, lambda, mu2, mu1. And the same, plus gamma, mu2, sigma, lambda, t, mu1, lambda, mu1. Right? For every lower index, we get a minus sign. So again, gamma. And now we have the sigma in mu1 will be in the lower index. Then the dummy index up, lambda, and that will be t, mu1, mu2, lambda. There's nothing much else that you can really do. And that is a tensor. So we reached what we wanted. We extended the idea of covariant derivative, of derivative, which we need, to curved spaces. It's the covariant derivative. Questions?
Integration basically would be the same idea.
So there's a volume elements you have to make sure you have this sort of G series. In principle, yes, but it's much less interest because most of the equations we write down in terms of differential equation. So to know how to write down the equations properly. Importance of this derivative and the derivative of the metric. I want to emphasize one thing, right? Again, why do we want to work with vectors and tensors in the first place? Because we know the transformation law. In a more basic sense, that means that we are not sensitive to the coordinates. So the importance of these derivatives, the importance of everything we do here, is that we're able to write down physics in a coordinate independent way. Always put coordinates. It's handy for us. But physics itself is not going to be dependent on these coordinates in any way. Okay. Covariant derivatives is a way of extending the notion of derivatives. It enables us to do works in any curved spaces. And of course, they have the general properties that we expect from derivatives. So properties of covariant derivatives. So one, they're linear. What does it mean that they're linear? If we take two tensors, T and S, and two scalars, alpha and beta, then alpha T plus beta S, U, lambda. Is what?
Alpha T lambda plus
Alpha T lambda plus beta S lambda. Okay. These are tensors. These are numbers. It's quite straightforward to check using the finishes. They obey the product rule. Covariant derivative of two tensors. Covariant derivative of the first tensor plus the covariant derivative of the second tensor. Or if you want, ds lambda is t lambda s plus t s lambda. What's the covariant derivative of the metric tensor?
They give us the geodesic equation.
No.
Maybe 0.
0. Why? Still, that just shows that it's still not. You need to think a little bit more about it. Why this is 0? Let's examine what I just said. Just have to see. What is the metric in flat space-time? Special thing.
Just the Minkowski.
What?
Minus 1.
It's constant, right? So what's the derivative of that metric?
0.
0, right? Now, derivative, what did we say about covariant derivatives? They are tensorial, right? It's a tensorial equation. So if it's true in one frame, it will be true in any frame. That's the whole point of tensorial equations. Now, of course, you can simply do the calculation. Select the frame you want. Even actually, you don't need to just plug in the definitions of the lambdas, and you'll see that everything cancels. Now, because this is so important, there's a name. This is called metric computability. Which we will make use to somewhere down the line. Similarly, G mu lambda is what?
Also
0, of course. Delta
0.
0. So, covariant derivatives. This one converts tensors to tensors. Right? We start with a tensor, we take its covariant derivative, we end up with another tensor. Okay? 2. In the absence of gravity, namely flat space-time, Cartesian coordinates. You're right that if it's not Cartesian, it's a bit more tricky. Gamma, when mu equal to 0, and then what do we get? But it reduces to normal derivative. These two things actually give us a very simple way of incorporating all the effects of gravity in the physical system. It's actually simpler than you even imagine. So what do you do to incorporate gravity into a physical system? What do we do? First thing, we write the equation that we know describes the physics without gravity. So in special relativity. We did not waste time in the first few weeks of the semester. So write an equation that describes a physical system without gravity. in special relativity. After we have the equation, what do we do?
Change the derivative to
We basically need to do two things. Eta mu mu. G mu mu, comma to the circle. That's it. Change derivative to covariant derivative. Equation we get after we do it. Remember when we started this test? It's going to be generally covariant equation, preserves its form, looks exactly the same. It's true in the absence of gravity, right? So according to the principle of general covariance, it's going to be true as well. That's it. Very simple. Magic. Right? That's all you need to do. So, according to the principle of general covariance, this equation will be true in the presence of gravity. Right? Yes.
From a physics point of view, what is the limit of the affine connection?
There's no unit.
So how can it be? Because when I'm thinking about the derivative, I'm taking
It's a mathematical entity.
yes. This is
What's the units of G? Doesn't have any. The units are not carried by G. They're carried by the coordinates.
But if I want to apply it,
If I write down the S squared, G mu mu, dx mu, dx mu. These are the units. This is just, think of it in terms of a matrix, right? Which tells you what is the shortest distance.
okay.
It doesn't carry any units, just a mathematical object.
But if I'm thinking about the derivative of the vector, which has units,
Yeah, but the units will be carried by the vector itself.
but I don't understand how the units can be the same in both sides of the equation, because you're taking the derivative, you're changing the
They are carried by the vector themselves. Carried here.
But T have some units, the tensor have some units, the affine connection don't have units, so this is all have units of T.
Yes.
The other side of
You
the
mean
equation,
because of the derivative? Well, they
Yes.
still be carried by the x mu here.
okay.
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 So it's still unitless. Now, before we go, I was hoping to do a little bit more, but I'm not sure how it's. There's some mathematical things, so I'm not sure if I should do it or should actually do it. But there is one thing which is important. Well, the thing, to give you a little bit of insight before we go home, the meaning of a derivation. Okay, I want to give you a little bit of an insight of what does it really mean, and why do we need this fine connection. So let's take flat spacetime. Flat spacetime, it's a good enough spacetime. Okay? And I want to look at the derivative of a vector. Right? So derivative of a vector in flat spacetime. I have 2 points, x mu plus dx, right? And it's alpha, doesn't it? And I have a vector v, which is an x alpha. X mu. And I want to look at the derivative of this vector. What do I really do? I look at this vector, but not at that point, because I know what is the value. I look at the vector at the nearby point, x plus dx. So this is v, x mu plus dx. And I need to take the difference, delta v. But I don't know if you've noticed it, I really do 2 things. I make 2 steps when I take the derivative. The first step, I take the vector and I transport it parallel to itself back to the original point, x mu. This is a v transported. This is step 1. And then at step 2, I look at the difference, delta v. Right? So really, what I did, you don't really notice that, right? But when I take a derivative of vector, I'm making 2 separate steps. Right? After I evaluate the vector in the point that I'm interested in, x mu, and in the nearby point, x mu plus dx mu, I take this vector here, I parallel transport it back to its original point that I'm interested in, and then I take, using the parallel whatever rule, change. Now, generally I don't think of the vectors being changed. But now what happens if I have the same flat space-time, but I decide to describe it using polar coordinates, r and theta. So now I have a point, let's see this one, this is x mu, x alpha. And let's say that now I have a vector, it's a different point. So this is x. X alpha plus dx. Now you see that I've drawn specifically the coordinates at these 2 points. Now when I do a parallel transport, I have to transport it back to the first point, right? What happens now to the transported vector? Parallel to itself. It has to be parallel to itself. Otherwise there's no point in making the difference. Right? What happens when I do it?
Components don't fit.
They do fit, they just change. The components of this vector relative to the coordinates don't change because the coordinates themselves are now rotated depending on the point in space I am. What takes care of that? Not exactly this extra chain. Exactly what the affine connection is doing. Taking care of the change in the components of the vector as I'm transporting it from one point to the other. That's why I need this extra term when I do the covariant derivative. Okay, so that gives an intuition. That's why it's called affine connection. It connects 2 points. Okay. start saying that. Okay. I have got more to say about that. It's very nice because it gives you the right intuition of what you think really is. But I think this is very easy to think of that in these terms, because you can visualize it. Okay, we think we pretty much ran out of time. We can take another 15 minutes, but maybe not sure how to organize the next lecture because I have, well, maybe more. I may need another. Okay, we'll see. Maybe I'll do like 1 hour myself and 1 hour tutorial on Sunday. Or I'll just decide that I'll do everything myself. We'll see. All right, any questions? No? Have a nice weekend. I'm going to get the next problem set now. And see you on Sunday.
כאילו כזה משולש כזה, זה כמו אוטו פרודקט פשוט?
אין דבר כזה משולש כזה. משולש כזה זה אות למדה. אות למדה היא מסמלת רק לא רק טרנספורמיישן.
וזה היה בלי אינדקסים, בלי כלום.
לא, אין דבר כזה.